We're the Q Lab at Harvey Mudd College, which is led by Professor Santana, and we are on the microfluidic subteam. Microfluidic devices have a wide range of applications, but we hope to design a microfluidic device that will be integrated into a bioprinter. They're useful in bioprinters because they have the ability to replicate gradients within the human body. So physical properties like density will vary as you move throughout the tissue in the human body. And we hope that our two-layer cross-channel geometry will be able to sufficiently mix and control the mixing of bioinks to replicate this gradient. And the two-layer cross-channel geometry aims to mix fluids efficiently at low Reynolds numbers, which is more difficult since fluids at low Reynolds numbers have the tendency to move in a streamlined manner in a laminar flow as opposed to moving chaotically.
We model bioink flow using ANSYS Fluent to evaluate the performance of the mixers. To start off with, using a rheometer, we found the viscous properties of 60% weight aqueous solution of 4-arm peg acrylate, and that data is shown in the plot on the left, where it's fitted with Newtonian and non-Newtonian models. We then populated ANSYS Fluent with the fitted model of dynamic viscosity and used this to run our simulations. These simulations started off with a mesh refinement study to find the optimal mesh size. And we followed the process in the flow chart right below that statement, where first in space claim we recreated our two-layer cross-channel micro mixer geometry, and then we adjusted it to fit various mesh sizes, which discretized our geometry into smaller geometries. And then we ran our simulations to find the volume fraction at different points. We then used this volume fraction data to calculate our mixing efficiency with the equation shown, which is a normalized version of our standard deviation of volume fraction at the outlet.
And so far in the mesh refinement study, we found that models with approximately 4 million elements had sufficiently low error when compared to the exact value estimated from Richardson extrapolation. And with this fine enough mesh size with accurate results, we were able to run concatenated simulations, which involved setting the output conditions as the inlet conditions of the next mixer and doing this in a sequence. And we found that at the outlet of the fifth mixer, there was a mixing efficiency of greater than 95%, which is the threshold we are looking for when mixing bioinks of low Reynolds numbers. And once we're able to implement this microfluidic mixer within a bioprinter, we'll be able to tune the properties of the printed hydrogels on demand to create more biomimetic structures. So in the future, and what we're currently working on is experimentally validating our simulated data, which involves imaging a PDMS fabricated micro mixer with an inverted bright field microscope and using dye to visualize the difference in the bioinks and see how they're mixing. And once we ensure that our computational model is indeed accurate, we are continuing to vary the geometry to find the optimal geometry for having the highest mixing efficiency while maintaining a relatively low pressure drop so that the microfluidic mixing device can easily be integrated into a bioprinter without too much loss of pressure, which could lead to difficulties in printing. Thank you for your time. We appreciate you listening to our presentation.